Swayam Prabha. Digital India. Educated India.
Now, we are going to discuss finding the multiplicative inverse. We come across the Euclidean algorithm can be adapted to find the greatest common divisor of two polynomial, and the extended Euclidean algorithm can be adapted to find the multiplicative inverse of polynomial, and specifically the logarithm will find the multiplicative inverse of b of x under modulo a of x if the degree of b of x is less than degree of a of x, and check it out, the greatest common divisor of these two polynomial function which is equal to 1, then a of x is a irreducible polynomial, then it has no factor other than itself or 1. So, the GCD of a of x comma b of x equal to 1. So, this algorithm can be characterized in the same way as we did for the extended Euclidean algorithm for the integers, and given polynomial a of x and b of x with the degree of a of x is greater than the degree of b of x, we wish to solve the following equation for the values of v of x, w of x and d of x, where d of x is the greatest common divisor of a of x comma b of x. So, a of x into v of x plus b of x into w of x equal to d of x, it seems to be a linear Diophantine equation structures. Once it comes under linear Diophantine equation structure, we have to find out the d of x, and if d of x is 1, then w of x is a multiplicative inverse of b of x under modulo a of x, and we have to calculate the following statement of the extended Euclidean algorithm for the polynomial. Now, we have to take the linear Diophantine equation a of x equal to a of x into v minus 1 of x plus b w minus x. It seems to be a linear Diophantine equation, and we have to calculate v suffix minus 1 of x equal to 1 and w of minus x equal to 0, so that the remainder is r suffix minus 1 of x is equal to a of x. And if b of x equal to a of x into v naught of x plus b of x into w naught of x, which is equal to b of x, then check it out, v naught of x and w naught of x. If v naught of x equal to 0 and w naught of x equal to 1, and then in this case r of x, r naught of x is equal to b of x under congruence of this value. So, it seems to be that extended Euclidean division algorithm, and then next we have to calculate r1 of x into a of x into v1 of x plus b of x into w1 of x, and divided by what the division algorithm of a of x equal to q1 of x into b of x plus r1 of x, and then check it out, the residue that is called as a remainder, and a remainder should be identically equal to a of x if under modulo b of x, and here q1 of x is a quotient, and then we are dividing what a of x and divided by b of x, so that r1 of x will get it, and then under modulo of b of x it holds good, so that we already calculated v1 of x, and v suffix minus 1 of x into q1 of x into v naught of x equal to 1, and so that w1 of x equal to w suffix minus 1 of x minus q1 of x into w naught of x, so which is equal to minus q1 of x. So, proceeding in this way, we have r2 of x equal to a of x into v2 of x plus b of x into w2 of x, and then if r2 of x is identically equal to b of x under modulo r1 of x, therefore, q2 of x is quotient of b of x divided by r1 of x, and then b of x equal to q2 of x into r1 of x plus r2 of x is a corresponding equation, so that we have r2 of x equal to a of x into v2 of x plus b of x into w2 of x. So, we can calculate V2 of x equal to V0 of x in minus Q2 of x into V1 of x, and W2 of x equal to W0 of x minus Q2 of x into W1 of x, and then R3 of x equal to R1 of x under modulo R2 of x, and Q3 of x is equal to quotient of R1 of x by R2 of x. Therefore, R1 of x equal to Q3 of x into R2 of x plus R3 of x. From this V1 of x equal to V1 of x minus Q3 of x into V2 of x, and W3 of x equal to W1 of x minus Q3 of x into W2 of x. Therefore, R3 of x equal to A of x into V3 of x plus B of x into W3 of x. Proceeding in this way, and we have a recurrence relation of Moore's general form, and end up with what Rn of x. So, Rn of x is equal to identically equal to R suffix n minus 2 of x under modulo of R suffix n minus 1 of x of the equation Rn of x equal to A of x into V1 of x plus B of x into W1 of x. So, that we can calculate quotient. The quotient is R suffix n minus 2 of x by R suffix n minus 2 of x. So, that R suffix n minus 2 of x equal to Q1 of x by here Q1 of x or n minus 1 of x, and then plus R1 of x. So, Vn of x equal to V suffix n minus 1 of x minus Qn of x into V1 V suffix n minus 1 of x, and Wn of x equal to W suffix n minus 1 of x minus Qn of x into Wn minus 1 of x. So, that Rn of x we can calculate. So, if you have devices from Rn of x of R suffix n minus 1, and we have a quotient is equal to exactly divisible, that is R remainder is 0. In this case, R suffix n plus 1 of x and R suffix n minus 1 are equal. So, that R suffix n minus of x equal to Q suffix n plus 1 of x into Rn of x. So, we got the d of x and b of x and v of x and w of x. So, this way we can calculate the quotient, remainder, and then how the reducible and irreducible polynomial we can write in terms of the division algorithm and extended division algorithm for the polynomial equation. Now, the table 5.4 shows that the calculation of multiplicative inverse of x power 7 plus x plus 1 under modulo polynomial power x. So, the inverse of x equal to x power 7 plus x 1 inverse equal to x power 7, that is if you have x power 7 plus x plus 1 into x power 7 under modulo of this equation, we have identically equal to 1. Therefore, one is a inverse of the other we can calculate. So, for computational consideration, a polynomial f of x in gf of 2 power n, where f of x equal to a suffix n minus 1 into x power n minus 1, a suffix n minus 2 into x power n minus 2 and so on a naught equal to summation I varies from 0 to n minus 1 into a I x I, can be uniquely represented by sequence of its n binary coefficient. Thus, every polynomial in gf of 2n can be represented by n bit number. So, the table 5.2 and 5.3 shows that the addition and multiplication table of Galois field of 2 power 3 under modulo m of x equal to x cube plus x plus 1. Table 5.2 shows that the binary representation. Table 5.3 uses the polynomial representation. Now, for addition, we have seen the addition of a polynomial is performed by adding a corresponding coefficient. In case of polynomial over Z2, the addition is just the XOR operation. So, the addition of two polynomial in a Galois field is corresponding to bitwise XOR operation. Now, consider the two polynomial in GF of 2 power 8 from our earlier example. F of x is a 6th degree polynomial, consider x power 6 plus x power 4 plus x square plus x plus 1, and g of x is x power 7 plus x plus 1. Now, if you add them, so x power 7 is 1 times comes, therefore, x power 7, and then x power 6 1 times x power 6 will come, x power 4 1 time, and then x square. Now x plus 1 it will be 0 because polynomial notation corresponding this value it becomes 0. So, now you converted into binary notation. So, for unit 1 for x term 1, for x square term 1 and x cube 0, x power 4 1, x power 4 1, x power 5 0, x power 6 1, there is no x power 7. Similarly, here x power 7 is 1 and x is 1 and 1 is 1. Therefore, we have what the XOR notation of the operation. So, 1 plus 1 0, 1 plus 0 is corresponding, you have to do that, and then we have a binary operation like start from 1 and then 1 plus 1 and corresponding 0 and then 1 and 0 1 00 will come. This is the binary notation corresponding to XOR notation. So that so we have a 57 value corresponding to this value, and this value is corresponding to 83. This is hexadecimal notation. So, one value will come, that value is D4. A moment thought should convince you that equation 5.4 is true. If you are not sure, divide it out and general Galois field of nth degree of polynomial of p of x. So, we have x power n mod p of x is p of x minus x power n. Now, consider the polynomial of gf of 2 power 8, which has the form f of x equal to because 2 power 8 it start from 7, 6, 5, 4, 3, 2, 1 and not corresponding to x power 7, x power 6, 5, 4, 3, 2, 1, 0. So, if you multiply by x, we have what x into f of x is b7 into x power 8, 7, 6, 5, 4, 3, 2 and 1 of under modulo of x. So, we have a extended Euclid of the 8th degree polynomial and 7th degree polynomial. Initially, you have a of x equal to so and so, and here v suffix minus 1 is 1 and w suffix minus 1 is 0, like that you have to initially start, and here b of x is, this is a of x and this is b of x, and initial value you have to consider like that, then the theory starts with the help of the table. And if a of x by q of x, a of x by b of x, and then we have a remainder quotient and a remainder, and then we have a what q1 of x is x, and we have a remainder r1 of x is equal to x power 4 plus x cube plus x square plus 1. So, from this we can infer v1 of x equal to 1 and w1 of x equal to x. Then comparative study with what next iteration. So, here if you divide this q1 into v1 plus r of x technique you have to do, q2 can generate it with the help of the table value. So, q2 of x will get it and r2 of x get it, and v2 of x and w2 of x also we can generate it with the help of the table already we discuss. So, here remember this table so that we can understand remember this table we can understand that the following problem. So, keep it in mind this, and then how we can calculate r1 of x and q1 of x and w1 of x and v1 of x and so on. So, that one can be divided other, and then we have a what iteration 2. So, iteration 3 also do the same process. So, q3 will get it, r3 will get it, v3 will get it, w3 will get it, and if q4 of x equal to x and r4 of x equal to 0. So, v4 of x equal to x power 7 plus x plus 1 will come. Similarly, w4 of x can get it, and d of x and r of x will be the same. So, from this we can infer that the GCD is 1, therefore, stop the result. So, W3 because remainder is 0, so stop the result, and then we can write directly from W of x equal to W3 of x and under modulo is x power 7. So, if B7 equal to 0, then the polynomial of degree less than 8, which is already reduced the form and no further computation is necessary. If B7 equal to 1, then reduction under modulo m of x is achieved using the equation 5.4. Therefore, multiply x into f of x, so that B6 x power 7, B5 x power 5, this value will get it into plus x power 4 plus x cube plus x plus 1 will come. For the multiplication, there is no simple XOR operation that will accomplish multiplication of GF of 2 power n. However, a reasonably straightforward, easily implemented the technique is available. We will discuss the technique with a reference of GF of 2 power 8 using m of x equal to this, which is a finite field used AES. The technique is readily generalized of GF of 2 power n. So, the technique is based on the observation that x power 8 under modulo of m of x equal to m of x minus 8 x power 8, which is equal to x power 4 plus x cube plus x plus 1, that is a technique based on this observation, and it follows by x and we converted into binary and can be implemented as a 1 bit left shift followed the conditional bitwise XOR with 0 0 1 1 0 1 1 from this, which represent the equation, and we summarize x into f of x as from these have B7 is 0, and then we have to take the coefficient B6, B5, B5, B4, B3, B2, B1, B0. If B7 equal to 0, then B6, B5, B4, B3, B2, B1, B0 into 0 of XOR with along with binary bits. If B7 is equal to 1, then we have a expression like this. Now, it is an earlier example we showed that f of x equal to a function you take it x power 6 plus x power 4 plus x square plus x plus 1, and g of x equal to x power 7 plus x plus 1, and m of x equal to x power 8 plus x power 4 plus x cube plus x plus 1. So, from the repeated application of equation 5.6 by adding intermediate results, we have GF of 2 power 8 can be achieved. Now, f of x converted to binary bits and g of x converted into binary bits, and we have to determine the multiplication by powers of x, so that if you multiply this value into this, you have what the resultant will be like this normal multiplication and using the binary bit, so that the resultant will come like that. And then if you start with 1 0, if you start with 100, if you start with 1000, 10,000 and 1 lakh, 10 lakhs, 1 crore, like that mean the bits. Just I am reading in terms of the numbers. Actually, you have to read 1 0, 0 0 0 1 0 0 5 0 followed with 1 0 0, like that you have to do of this multiplication, so that if you add this number to this, you can get it like this, and then if you multiply in the resultant, if you XOR notation, you have to do like this, and then finally we have a multiplication of this is equal to what this number into this number, and then this number into this number, so that which is equivalent to the resultant is x power 7 plus x power 6 plus 1 will come. So, this way we can find the Galois field or representation binary bits, polynomial to the binary, binary to the corresponding equivalent irreducible polynomial of GF of 2 power 8. Now, we also using in the cryptography using the generator. So, the equivalent technique for defining the field form of GF of 2 power n is same irreducible polynomial. Sometimes it is more convenient to begin. We need some definition of generator of G. Already we explained generator of G, the same in terms of the finite field. So, generator G of a finite field f of order q contain q elements, and whose first to q minus 1 powers generate all the non-zero elements of f. That is, start from what q element is, therefore 0 to q minus 2, consider the field f defined by f of x, the polynomial, and element b contained in f is called the root of the polynomial if f of b equal to 0. Finally, it can be shown that the root of G is irreducible polynomial generator of the finite field defined on that polynomial. So, that consider the finite field GF of 2 power 3 over irreducible polynomial x cube plus x plus 1 discussed previously. Thus, the generator G must satisfy f of G equal to G cube plus G plus 1. So, keep it in mind as discussed previously that we need not find a numerical solution to this equality, rather we deal with the polynomial arithmetic with arithmetic on the coefficient is performed under modulo 2. Therefore, the solution preceding equality is G cube equal to G plus 1 or minus of G plus 1 minus G minus 1, and it shows that the generator of the polynomial of degree less than 3, we have the following. If we have G power 4 means G into G cube is G into G plus 1, G into G is G square plus G. So, that G power 4 can be written as G square plus G, and G power 5 is G into G power 4, which is equal to G into G square plus G, because G power 4 is G square plus G. Therefore, G into G square is G cube and G into G is G square. Therefore, G cube is G square plus G plus G square, and G cube is G plus 1 and G square keep G square. So, G cube plus G square is G square plus G plus 1, and G power 6 is G into G power 5. Therefore, G into G square plus G plus 1 equal to G cube plus G square plus G. So, it becomes G cube is G square plus G and G square keep as it is. So, what happened from the previous, we have what we can apply G cube as G plus 1 keep as it is. Now, we have here G cube plus G square plus G. So, replace G cube as G plus 1, this G keep as G square keep as it is, this G cube as G plus 1 plus G is the what get cancel, then G square plus 1, and G power 7 is G into G power 6, which is equal to G into G square plus 1 previous taken. So, G into G square is G cube and plus G, and G cube is G plus 1, G cap is keep as it is, G get cancelled, therefore 1. So, 1 is nothing but G power. So, we can write the generator like that, and the powers of G generate all the non-zero polynomial of GF of 2 cube. So, it shows that G power k is equal to G power k modulo 7 for any integer k. Therefore, table 5 shows that the power representation as well as the polynomial and binary representation, that is Galois field of x cube plus x plus 1 can be written, power generation is first 0, the polynomial is 0 and corresponding binary representation is 0 and decimal representation is 0. G naught means G power 7, because GF of 2 power 8, right. Therefore, G naught equal to G power 7 and polynomial representation is 1 and corresponding binary representation 0 0 1 and decimal representation 1. G power 1 is G and binary representation 0 1 0 and decimal representation 2. G square is G square and 1 0 0 is representation of binary and decimal representation 4, because 0 into 2 power 0, 0 into 2 power 1 and 1 into 2 square, therefore 4, and g cube is g plus 1, because x cube plus x plus 1 representation, therefore g power 4 g cube is g plus 1, that represent 0 1 1, corresponding decimal representation is 3. For g power 4, g square plus g is 1106, and g power 5 is g square plus g plus 1 and 1117, 7. G power 6 is g square plus 1, 101 and 5. So, this way we can represent the generator of GF of 2 cube, and we can do with the help of the multiplication to multiply in the power notation, add exponent modulo 7. For example, g power 4 into g power 6 is g power 4 plus 6 is 10 under modulo 7. So, 10 under modulo 7 is 3, therefore, g cube, and g cube is equivalent to g plus 1. The same result is achieved using the polynomial arithmetic. We have g equal to g square plus g, and g power 6 is g square plus 1, therefore, g square plus g into g square plus 1 equal to g power 4 plus g cube plus g square plus g. So, we can determine g power 4 plus g square plus g cube plus g square plus 1 under modulo g cube plus g plus 1 is simply divide g power 4 plus g cube plus g square g divided by g cube plus g plus 1. Therefore, 1 times of g is g power 4, g square g will come, get cancelled, and then we have g cube, and then we have required number is g plus 1, because g cube comes, therefore, g plus 1 represent. So, the value of this division is g plus 1, which agrees obtained using power representation. The table 5.6 shows that the multiplication of the table of GF of 2 cube, and using power representation, note that this yields the identical result to the polynomial representation with sum of the rows and columns interchanged. So, in general, GF of 2 power n with irreducible polynomial f of x is determined. Therefore, g power n is f of g minus g power n. So, we can calculate the powers of g from g power n plus 1 through g power n minus 2. So, the element of the field corresponding to the power of g from g power 0 through g power 2n minus 2 plus the value 0. Therefore, for multiplication of two elements in the field using the inequality, using the equality g power k equal to g power k modulo 2 power n minus 1 for any integer k. Therefore, we have a summary. So, in this section we have shown how to construct a finite field of order 2 power n, specifically Galois field of 2 power n with the following properties. So, Galois field of 2 power n consists of 2 power n elements. So, the binary operation plus and multiplication are defined over the set. The operation addition, subtraction, multiplication and division can be performed without leaving the set, and each element of the set other than 0 has a multiplicative inverse. So, we have shown that the elements of GF of 2 power n can be defined as the set of all polynomials of degree n minus 1 or less with binary coefficients. So, each such a polynomial can be represented by a unique n bit value. Arithmetic is defined as a polynomial. Arithmetic modulo some irreducible polynomial of degree n. So, we have also seen that the equivalent definition of the finite field of GF of 2 power n makes use of a generator, and then arithmetic is defined using the powers of generator. Therefore, we have a table. So, GF of arithmetic using generator of the polynomial x cube plus x plus 1, and we have a bit start from 0 is corresponding this, 1 is 0 0 1, and a corresponding g is a general Galois field is 0 1 0, and g square represent 1 0 0, g cube represent 0 1 1, and g power 4 represent 1 1 0, and g power 5 represent 111, g power represent 101, and we have a table corresponding to this. Therefore, 0 1 g, this small g, right. Therefore, g square, g cube, g power 4, g power 5, g power 6. Simply we have to what multiply them. Therefore, 0 into 0, 0 into 1, 0 0 into something like that, we using the addition operation, addition operation. Once again I will tell you, and we have to use the table, Cali table with 0 addition operation under modulo. 0 plus 0 0, 1 g, g square g plus 1, g square plus g square plus g plus 1, g square plus 1, and we have for column wise 1 g, g square g plus 1, g square plus g square plus g plus 1, and g square plus 1. Now, we simply add 1 plus 1 is 0, 1 plus g is g plus 1, this is g, right, and then g square plus 1 will come, g cube plus 1 is g, right, g power, because g cube equal to g plus 1, therefore, it becomes g power 4 plus 1 is g square plus g plus 1, and g power 5 already we calculated, see previous expansion and then substitute the table. So, g power 5 plus 1 is nothing but g square plus g, and g power 6 plus 1 is g square. So, that we can calculate g associated with other. Similarly, we can go for g square, g cube, g power 4, g power 5, g power 6, add this, so that you can understand how we can do the addition of these two representation in terms of the polynomial, and then the arithmetic is using in the Galois field. And for multiplication also the same technique you have to do that, and then already we explained that 0 into 0, everything 0 here, and then 1 into 1 into this g, 1 into g, and then 1 into g square, g plus 1, everything 1 into same thing will come. Now, here g into g is g square, g into g cube is nothing but g plus 1. So, g cube equal to nothing but g plus 1, and based on this structure we can do the rest of them, and g into g cube is g power 4 represent g square plus g, g into g power 4 is g power 5, g power 5 represent g square into g cube is g plus 1, and to g square multiply and then, and using this you can get it the table value. So, similarly you can go to the g2, g3, g4, g5, g8. So, this way multiplication we can bring. This is the most general form of gf of 2 cube under multiplication operation. Thank you.